I know, I know. It looks like it's really cold in here with these on. Bloom's got earmuffs on. That's how cold it is in his room. Okay, actually, it's the warmest it is all day during this hour. Okay, so here's the deal. We are looking at pre-calc day 3. I promised that I would come in and talk about problems I, J, K, and L. These are currently on this year's notes and page 18. Now, we're looking at restrictions, okay? And on these restrictions, there are some little tricky things, and this is the trickiest one of them all. I mean, kind of restrictions. It really is. Don't look at me slant-eyed like that. What are you doing? You mad at me? Okay. All right. So we have 5x minus 3, and we have x squared plus 2x minus 3. If I factor this, I come up with this. And I'm able to find my VAs, my vertical asymptotes, that x is equal to -3 and x is equal to 1. But I'm also interested in the restrictions that the square root comes through with. Those restrictions, I can't have the stuff underneath the square root be less than 0. So I'm going to talk about that. So my restriction underneath, I'm not drawing a line through it since my board's that bad, okay? But x is greater than or equal to 3/5. Well, I just found out that I have vertical asymptotes from this function because of what's being divided at x equal -3 and x equal 1. But it says here that the stuff underneath my square root doesn't start until 3/5. What should I do with my domain restrictions? I mean, most of the time you say, well, x can't be -3. But would it matter? Yeah. I don't include it. I don't include it because this -3 is way off over there. It's further out there than an outlier on this. And the reason why I don't include it is because -3 is way the heck less than 3/5. Okay, and that's really where I should start. I'm starting at 3/5 and going on. So if I'm looking at interval notation, that makes a lot more sense, that I wouldn't even cross 0. I mean, how the heck would I get the -3 if my man going across the negative tracks? Okay, so I've got 3/5 to 1 because that's my other asymptote, my vertical asymptote, and starting at 1 to infinity. So in this case, I dropped that other vertical asymptote because I'm not even worried about it. The rest of the function's taken care of on the other side. Okay, are we okay with y? Now, in this next one, please notice that the x is not under that square root of. Okay, so that's not a restriction. And I'm looking at this one, and it's positive all the time. Okay, I shouldn't say positive. It works on any domain I provide in it. Okay, and because the x is outside that square root of. If we were inside, whole different ball of wax. But because it's outside, it goes from -infinity to infinity. Are there any questions on the difference between those problems? Okay, have you noticed that the restrictions really happen when the x is underneath the square root and or in the denominator? Other than that, have at it. It works all the time. Okay, so those are the things I've got to be paying attention to. Now, I'm going to use some skills that we learned in chapter P. Okay, here. What I do know is that my restriction is being driven right there. That 4 times what's inside there, not a big deal. +4, not a big deal. It's what's inside that square root. And if I think about what's inside the square root, I'm just going to graph the stuff inside the square root. Okay, this is not a graph of the function I have. This is a graph of the stuff inside the square root to help me answer this question. So when I'm looking at this, if I bring it up, I'm really concerned with x squared minus 4 being greater than or equal to 0. Well, if I factor that, and I break that down in factors, x minus 2 times x plus 2 is equal to 0, I realize that not only do I have my places that my graph crosses the x-axis at -2 and 2, okay, -2, 0, and 2, 0, but I start thinking about where is my function always positive, okay? So where it's positive. Well, it's positive from -infinity to -2. And it's positive from 2 to infinity. Do you see that when I bring those in? So that's where my function's positive or 0. And that's significant because that's my restriction when I'm talking about my D, my domain, okay? Because it's positive less than -2, it's positive greater than -2. My interval notation restriction explains it that way. So remember, I have a choice between set builder and my interval notation. I'm showing both of them, so you guys are used to seeing them both. You're writing them both down, and we're going to be required to do one or the other in problems. Are there any questions about what I just did? Okay, now for those folks that did the question, you're already done with this next one. For those folks who didn't, this next one is very similar. I already gave you the graph. Go ahead, look at what's there about the restrictions and see what you can come up with. Go. Okay, so here we're looking at this, my domain restrictions really being driven by 4 minus x squared. I have the graph provided what 4 minus x squared is separately, but I'm going to factor that out. And I got 2 minus x and 2 plus x. So I've got those going on. And so again, I've got my x zeros, my x-axis crosses at -2, 0, and 2, 0. But now I got to ask my question because I'm looking at something underneath a radical. All that's got to be positive. Well, when's that positive? If I really look at the idea where that's positive or 0, it's right there between -2 and 2. Okay, that range. And remember, this is not a graph of the function. It's a graph of the members of the function inside that square root, for lack of a better way to talk about it. So I'm looking at this idea that x is a part of -2 to is less than or equal to x, which is less than or equal to 2 if I use set builder. If I use interval notation, I go -2 to inclusive. Okay? Are you okay with my solution? That's my domain restriction. That's the only place it'll work. Crazy, really tight domain, right? Are there any questions about what I did? Now remember, we've been working on domain restrictions. We've been doing some funky stuff. Now we're going to catapult ourselves onto, what, page 19 is it? We started talking about continuity. Did we talk about boundedness? So we're on example 7, I think. If we can get there, maybe. People are like, example 7, where is it? I don't think we've talked about this. I think we're here today, right at the top. Okay. So I appreciate you bouncing around today. In notes today, it's on page 24. Okay, thanks for having that open. I read upside down okay sometimes. Okay, we're looking at page 24. We're talking about a restriction about boundedness. And remember, when we're doing boundedness, if it continues going up, it's unbounded. It might be bounded below, on both sides, or it might be bounded above, and, or it could be bounded, depending on what the functions are looking like. It's all about the graph itself if we look at it. We can explore it if we wanted to on tables, and table doesn't go higher than the value, we can probably figure it's bounded above. It doesn't go lower than a certain value, we can probably figure out it's bounded below. But the visual really helps us do it faster. Now, we have a graph here that's actually put in, but we're talking about bounded on an interval. And I want to just talk about this because sometimes they'll break a graph up and they'll define the domain of what the graph is that we're looking at. In this particular case, if I look at the whole graph from -infinity to infinity of this f of x equals 1 over x graph, it's unbounded because it keeps going on to positive infinity and comes out at -infinity. I mean, there's no restrictions on it. It just keeps going on. Well, it has a restriction. X equals 0 is a vertical asymptote. But when I'm looking at the idea of limiting my domain, okay? So if I talk about limiting my domain, if I just want to look at this first part, oh, I can't use that, can't use blue. Let's use red. If I use this first part, if I say I want to know between -infinity and 0, okay? Let's talk about just that part of the graph. Matter of fact, if I was going to do it visually, I probably should look at the screen being this. Because if I just covered that up and said, hey, that's the axis, everybody would be looking at it, was like, Bloom, that looks like it's bounded above. It's got a horizontal asymptote at y equals 0, okay? And that would be true, okay? It's bounded above. on this interval. But if I look at it from the other side, okay, if I look at it from the interval from 0 to infinity, on this function, the very same function is bounded below. Does that make sense? When I decide to define my domain, that I can talk about the different ways a particular function is bounded or unbounded? Does that help? Yes or no? I have stairs. It's always scary with stairs. That's my graph, and that's what we just talked about. Okay, and I can restrict it, to the interval we wish to consider if we need to. Okay, we can have that restriction. Bounded above on an interval from negative infinity to 0, and bounded below on the interval 0 to infinity. But remember, right now, I want you to be aware that they can break it up. In this particular problem, we're just looking at an example. I wanted to do that because sometimes you'll come across a reading and say, well, it's bounded below here, it's bounded above here, and I wanted to make sure that you have an idea what that means. But this graph itself, unbounded, from negative infinity to infinity. Does that make sense? Okay, but I have to restrict the domain to talk about it being bounded in either side. Now, with that said, wow, I didn't know I could change colors. I got to figure out what tap does that. Okay, all right. So here's the deal, checking boundedness. I can put that in my calculator. I'm pop it in my calculator. I just found that 0, -4 is my vertex. Okay, I just did that. 0, -4 is my vertex. Now, thinking about this, identify each of the functions as bounded below, bounded above, or bounded. What do we know about this now? Does it keep going up all the time? So it's not bounded above. Does it keep going down all the time? No. Okay, it's bounded below. Matter of fact, it has a absolute minimum of -4 at x equals 0. Okay, and we're going to be talking about that next, talking about maxes and minima. But right now, it's bounded below at least. Oh wait, I have that below because it's bounded below. That would make sense. Okay, bounded below, lower bound is -4 in this case. Lower bound being the y value. This next one, I ran these on your calculator earlier today. I did maxima. I'm not sure, have you guys worked with max and min on your calculators? Those people at home, don't raise your hand, I can't see them. But the folks in class, go ahead, pop them up. Have you guys worked with max and mins on your calculators? I got 1, 2, 3, I got 5, so 6. Okay, good. All right, so I'm not going to worry about reviewing that. We're just going to go in and use it. Okay, remember, I can look this up on my calculator. If I actually use the min program in my calculator and I'm working on the max curve, it'll freak out on me, or vice versa. So I got to make sure I know which one I'm looking at the time. Okay, so selection's a big deal. So make sure you're reading. But I did find these points out by using my max and my min, and these are absolute max and mins on this function, and it's an absolute when there's nothing bigger or nothing smaller. It's local when there's plenty things bigger and plenty things smaller. All right, and that kind of goes into the idea local is relative to other things being compared to. So keep that in mind. If you read something that says relative max, relative min, it's the same as local max, local min, loosely, okay? But here, because I've got this up and down, I've got this function is bounded. Bounded above and below, upper bound is 1/2, lower bound is -1/2. Now, I've talked about my maxima, minima, kind of locally and absolute in these. But when we actually are asked to find them, I actually have a format I want you to start using. I can get this. For some reason, this doesn't work real well for me today. So I'm not sure why, but last year when I set it up, it worked no problem. But I still want that highlighted. I want to make sure you recognize that writing your answers using the following format for max and min. Max is y coordinate at x equal x coordinate. Min is y coordinate at x equal x coordinate. Did you notice I want to identify my y, how far away from the axis it is, the x-axis, and then tell you, or you inform me what value of x that happens at. That is talking about your max and your min, and that's the format I want you to use when we're taking the test. We're doing a quiz, okay? I'm aware that in the past you just gave me coordinates of your max and min, but I want to dress it out this way and prepping you for the way you'll dress it out for calc. Now, local maximum, local minimum. Remember, local if there's something bigger than it or smaller than it. Absolute if there's nothing bigger or smaller than it. And then that bottom, I kind of talked about that. People are wondering why I'm going off about local maximum, maximum, absolute maximums, absolute minimums, and relative extrema, which means we're talking about the locals because relative means there's something more when I'm talking about it. Okay, so identify local extrema. Let's use our calculator to help us with that. This is my graph. Okay, by the way, how did I do that? I got a window, and my window was negative 20, 20 for my x's. My y's is negative 30, 30. Okay, so if you're wondering, and anywhere around there, I just did that so I can get my little bottom part of the curve in there. And then I did my x scale and my y scale where the hash marks happen on my graph are at 10. Okay, now the function I put in there, I've got x to the fourth minus 7x squared plus 7x. That's what's on my problem. Now, I can graph all sorts of stuff. Matter of fact, if I decide to drop something there, my fourth or my second, my calculator will still graph for me. It'll dutifully do what I asked it to do, even if I ask it to do the wrong thing, because it'll get it done. So pay attention to what you enter into your grapher. So please do that right now. I want you to graph this because we're doing max and min right now. So get that done. I want you to just pop that into your graph. That's a good question. I'll flip it back now that I have people on the same thing. Negative 20 to 20 for my x's. My y's were negative 30 to 30. But as long as you got the whole graph in there, you're all good. Okay, that's just kind of like, hey, look how big my window is. This is what we can see. Okay. So check that out. If you need a calculator, I got them on the back counter. Now, when I graph, I got this. When I check my max and min, second calc, I got max and min. I'm going to do min first because that's where I'm at. I'm going to go over there and hit enter. I got the right bound, left bound's always first. Now my right bound. Okay. And I have a absolute minimum at negative 24.057 where x is negative 2.57, negative 2.057. And according to what I just asked you to write it, that's how I'm writing it. Okay, and it's absolute because there's nothing smaller than that in this graph. Okay, it's local or relative when there is something smaller, okay, or bigger. Now, what I want you to do is to find the other two because we're practicing maximum minima, okay, and we're practicing the format I want you to do things in. So go for it. See what up. And if you got a graph different than mine, let's chat. I can almost guarantee you forgot to put that squared in the 7x part. Go grab one. Go grab one. So you should have found, hopefully, local minimum, local maximum. Okay, and they're local because there's something bigger or smaller. Okay, so keep that in mind. Absolutes, there's nothing bigger or smaller about it. Are there any questions about finding them and how I did? Remember, y is first, x is second when I do this. because I'm talking about how big it is and the distance it is. Clarifications? Mistakes? Fat fingeritis by Bloom? Let's just double check. I'm here. So now I've got this bad boy second. My next one, I want to go, I think it's maximum. So I'm going to go second trace. I want to go to max 4. And so I'm up here. I hit there, go over here. Anytime after I make my turn, I can get it. And it should be 1.3. And I have it down here, my maximum, 1.324. And at 0.456, yep. So it's kind of a little out of order, but I do my minimums together. And then I do my second one. That's another min. I'm over here, hit my enter. I move over again, make my corner. I get there, and I got negative 1.766 for 1.601. Okay, cool. I just had probably an order issue. I got to look for that too when I grade your tests. Are there any questions about that? All right, cool. Now, symmetry. You guys all took geometry. And in geometry, you learned about point symmetry. It's rotational symmetry when you can take something and rotate it 180 degrees about the origin, okay? Or about the figure itself. You go 180 degree rotation, it's called point symmetry. And people are like, why point? Well, point being the origin symmetry. If I can rotate a graph 180 degrees about the origin, which is really taking and multiplying everything in the graph by -1, that's rotation, okay? I get to recognize I have an odd symmetry. If I can have a graph cut in half by the y-axis, that's an even symmetry. Algebraically, what that means is this. Okay, for even functions, a function that has y-axis symmetry, I got f of negative x equals f of x. X and negative x give the same outputs that we have. Okay, should be on page 25, right? No, it did. I know what's on today's assignment. I saw that, but I also want tomorrow's short too, and we'll see how this works because I want to be done in the next 10 minutes. Okay. So we have f of negative x is equal to f of x. Notice this is parabola, okay? Even symmetry. So when I put the negative side of x in, the opposite of it, I get the same values out, okay? That's what this means up top, all right? I move that around. Now, odd function. I have rotational symmetry. People are like, what do you mean? If I rotate it 180 degrees and if it's about the origin, I got to get the 180. And unfortunately, it doesn't let me go about the origin. It's the same function going back to itself. But I know people are looking at me like, boom, that doesn't look like it's right on top of it. That's why I got to check it algebraically. Okay, I'll have an idea, an inkling in my head looking at a function. Okay, that looks like it rotated around to finish out the other half of the function. But I have to prove algebraically that it's working that way, okay? And I got to do the same thing with even symmetry, but even symmetry is easier to like see, to be honest. But let's see what it looks like algebraically. All right, so we've got this thing going on. I've got to see checking functions for symmetry. Tell whether each of the following functions is odd or even. Remember, this is even. Odd, this is my result. Look at them both. I have people get them confused every year. Every time you use them, you got to be thinking, why am I using this? Am I proving it to be odd, or am I proving it to be even, or am I just doing it because I'm doing it mindlessly? I want you to have a brain about it when you're doing this. So you got to think, for an odd function, I put in the opposite of my x value, and I take the whole opposite of the function, okay, as a result, okay? That'll have that 180 degree rotation, that odd rotation rotates about the origin. When I do an even function, that Ginsu knife, that samurai sword, cutting the function right in half on the y-axis, that's opposite of x goes in, and the same function results. So x squared, negative x goes in, negative x squared is x squared. The same function comes out. okay? So I've got to start recognizing what that sign change does and what happens inside the function, and I can probably start having an idea what the function is before I even start doing my algebra support. So my algebra support on this function, because I already see the picture and I've got this samurai sword cutting my function right in half, I'm pretty confident it's even, but what's it look like algebra-wise? Okay, so I'm not even going to use the odd one. I'm pretty confident it's even. So I've got this going on. Put the opposite of x in. So the opposite of x squared is just that squared. And I'm not changing the sign of the constant there when I put in the opposite of x. Okay, constant's all by itself, the sign won't change. X squared minus 3. Well, it's the same function that we started with. And because of that, I can say it's an even function. I gave the reasoning why. It doesn't make sense. Okay, look it over. It's not just getting it down, it's really understanding what's happening with it. Remember, that's an algebraic support for why I can say it's even. Okay, I'm looking for that on your test. Now, in a multiple choice test, I get that you're gonna, it's a speed test. It's a, hey, I've SAT, ACT, I gotta do this under time. I gotta get this going. How can we start looking at it? I want you to start looking at the fact that in an even function, if I don't have the picture of the function on my calculator, I don't really need to, because if it's a even power and my constant adds in, I got a pretty good chance for it being an even function, okay? Because of that, but I got to pay attention to what happens with my signs when I work through these. This next one, I talked about this in my last class, and I want to make sure you recognize this is what my function would look like if I flipped, oh, gosh darn it, where is it? There we go. I got to flip that back and undo stuff. Okay, now this is what my function, excuse me, we gotta freeze something. Okay, this is what my function would look like. Okay, and we had it rotated. If it's going to rotate about the origin, I'm going to rotate this, and I have that little dot to know where the origin should be pointed for my rotation. That's what the function should look like. So I know it isn't odd. Are you in agreement? I also know, because I slid my function's vertex off the y-axis, that it can't be even. Okay, I know it's not odd, I know it's not even. Okay, but I gotta prove algebra-wise that it is. But now let's talk about what I'm doing. When it's even, I plug that in, I get the same out. When it's odd, I plug it in and it's opposite out. Does that make sense? Those are my rules. So what I'm going to do, I'm going to put in the opposite of x no matter what each time. So I put in the opposite of x and I get this out. Okay, did my signs change on all the terms, or did the signs stay the same on all the terms? Those are the two things I'm wondering about. Even functions, the signs stay the same. Odd functions, all the signs change. Do I have either one of those with this? So I'm going to check it. I got a plus, a negative, a plus, a negative. Oops. It's neither, is it? Isn't it? And just to prove it, I'm going to talk about, hey, it's not even because it did not stay the same. And now I look into the opposite of that original function, and the opposite of the original function, all my signs should have changed, and that's not true up here, so it's not odd either. So based on that, it's neither. Are you okay with the idea of sign change for it being even versus odd? Okay, now switching the page. You guys got one more? Give it a try. Look at it. Remember, the first thing you do is plop in the opposite of x in the function, and you're investigating. Does it stay the same? Even. Okay, you're investigating. Does it change all the signs? Odd. Okay, and we're working with a fraction on this one, so let's pay attention to what's happening there. And I'm going to show you on this one. By the way, I made this with something that wasn't square, so it's not going to work real well. But my little sideline, I think, because of that 180-degree rotation, I'm thinking that's odd. Okay, so I have that odd thing in mind, and I got to prove it to myself. Is it odd? By showing my algebra work. Okay, so now, again, I put in the opposite of x into my function just to evaluate it. Okay, now I got negative x cubed all over 4 minus x squared. Now I got to keep in mind, is it the exact same function? Sign changed, right? So it can't be even. Now, did my function sign change? And remember, when I do that, it's just one. It's either the numerator signs change or the denominator signs change. They both can't change because that would be the same function. That would be an even function, because -1 divided by -1 is 1. Okay, so only one of them will change. So I'm looking this over, I'm checking this out, the opposite of h of x, and it's just my sign change. So that's what happens here. So these two are the same. So it's an odd function. Okay, and that's how I determined it. Along with the fact that I really felt it was going to be odd because I saw that 180-degree rotation about the origin. Okay, so I'm really just supporting my, inkling that I thought it was an odd function with my algebra. Now, I gave you functions with pictures, all right, which makes it a little bit safer and easier. It seems like they're funner because you're like, oh, I already know this. But most of the time, to give it a more difficult level for you, is I give you the function without a picture, because it relies on you being able to enter it into your calculator without fat fingeritis issues, okay? And also to give yourself support when you kind of are a little scared that it's not. But let's do some investigation. Let's talk about signs. When the signs change completely, it's odd. When the signs all stay the same, it's even, okay? In this one, will the +5 sign change if I put in the opposite of x? So right now I know it can't be odd. It's neither or even right now. If I plop in the opposite of x because it's a even power in the x term, that first term, will it change the sign or will it stay the same? It'll stay the same, right? So right now I'm thinking this function's even just looking at it. Well, let's follow through and dress it out. I got the opposite of x squared is just x squared, and so it's the opposite of x squared. My sign doesn't change. The signs are the same in the function. This is going to be and remember, this is all about the definition of even function right there. And now I can, hey, it's an even function. Now, just a little FYI, we're going down. We got 2 left. And then I'm going to do some basic cleanup, some of the stuff I've been saying about even and odd functions, and we're done with notes. Okay? Are you okay with this so far? I got some faces, you're looking at it like you're mad. Are you okay with it? We're doing okay? All right, good. Thanks for the smiles. All right. So, in this one, will my signs change completely if I put in the opposite of t? Okay? By the way, it's got to be cubed up there. For some reason, when I wrote this up, I forgot to cube it. My signs change completely. According to an odd function, I'm taking the opposite of everything and the opposite of everything there, and I'm just showing you this is the opposite of everything. I took the opposite of everything, I'm going to distribute through the function, and it's opposite of the original function. So and this is the definition of an odd function right here. So I know this function's got to be odd. And I'm just bringing it back in so you can see it again. I know it's great. I rewrote it. I'm re-talking about it and everything, but it really helps make sure every time you say a function's even or odd, you know what the definition of even odd functions are based on your algebra. Now, the last one. Y'all start the last one in G. We're doing G, and we're going to come back to those other ones tomorrow, okay? y'all start, think about what you're doing, think about what we've done, and see what you can do about making improvements. Remember, think about the definition. The first thing you do on every function is put in the opposite of the variable that's there. So the opposite of x goes in. When the opposite of x goes in on the numerator, okay, the first term changes sign, the second term changes sign, the third term stays the same. So it's not odd and it's not even because those things changed, okay? First term, that's going to change. Second term is going to change because they're odd powers. The last term doesn't change at all. The bottom terms don't change. So the bottom kind of evaluates as an even. The top evaluates as neither, okay? So if I'm looking at this and I talk about this taking the opposite coming through, I'm really looking at it's not even because it's not the exact same on top and bottom. And it's not odd because it's not a wholesale sign change all the way across on the top because that constant change sign did not change, okay? So that is a neither proof for us, okay? I got neither divided by even. Now people are like, oh, there's like this theme for stuff. So those three are done. Those are our basic three. We got 6 left to do tomorrow. We'll see if we just do 3 or 6. I'm going to pick some. I know they're kind of a lot, but I find that after you do a few practice, you get better at recognizing that sign change. Okay. Now, flip the page and read, because hopefully right now we got 3 things that you should know right now, guaranteed, because I've been repeating it over and over. And I'm hoping that you got them. You're going to do a little self-quiz. See if you got it. Make sure you got it like just put a little pen or write small and see which one's which. Okay? So on that next page in 27, that you guys are looking at that self-quiz. If none of the signs change, the function's even. Okay? And I got the definition up there. If all the signs change, the function's odd. If some signs change and some stay the same, you know, I like to collect them, they're fun, it's neither. Are you okay with those 3? Now, I don't know how you keep this in your head on how you get it going, about what drives the function when we have ratios or a fraction or a rational function, okay, or with a quotient. So even divided by even gives us an even. So I got an even function on top, an even function on the bottom. I'm dividing them. I get an even function result. If I've got an even divided by an odd or an odd divided by an even, I don't care if there's the numerator is even, denominator is odd, numerator is odd, or denominator is even, it'll be an odd function. Okay? Now an odd function on top, an odd function on the bottom, evaluates as an even function. Okay? I got neither over whatever, I don't care, whatever meaning odd or even, or neither again. And whatever odd, even, or neither divided by neither, remember, because it's neither in there, it's going to be neither as our final thing. And those are the rules for even and odd functions. Now, it's really important that we keep these in mind because when we get to chapter 4, second semester, we're going to be using it for sine, cosine, tangent, cotangent, cosecant, and cosecant, okay? Now, that's even and odd functions. I was supposed to determine functions, symmetry, even and odd. We are done for today. I apologize it took longer because of the issues that we had with my board, but hopefully things will go well for you in the assignment.